start recording now. And so we're going back to Zoom, apparently, but I'm going to do more examples in class. So let me just raise this a little bit. And the first thing that I want to show you is, here, let's just see. Yeah, here we go. And let me also fix this. And let me put this over here.
Is the returning to Zoom meetings something that is just for today, or is that going to be more frequent?
Okay, now what I want to show you is let's first make this a lot bigger. And but first I want to go over here and show you some Matlab tricks having to do with series. I mentioned them a little bit last time or in class, but it was only the last few days that I got in touch with or got an answer back from Matlab as to my question. So the simplest thing is, suppose you want to form a series and you're not too fussy. Well, then you just say sims x. That's telling Matlab that x is a symbolic variable. And then you say series, and then whatever your function is, in this case, log of 1 plus x. And then it will give you, in this particular case, it gives you this series. And for reasons that I don't understand, but I presume Cleve Moeller, I know Cleve Moeller understands and prefers, the sequence has this funny characteristic that it's backwards to what we would write. Also, for some reason, instead of writing fractions with numerator, straight line denominator, Matlab writes them as x squared / 2. Anyway, here's another example for, suppose we have, here, let me see if I can move that out of the way. Suppose we have we want to do, we make z a variable, might be complex. We then say series 1 over, so this is going to be a Laurent series or a Laurent series, 1 over e to the z minus 1. So this has a singularity at z equal to 0. And so then suppose we were doing it by hand, then we'd say, well, e to the z is, for small z, is 1 plus z squared over 2. You subtract 1, the 1's cancel. You factor out a z, you get 1 over z times 1 over 1 plus z over 2. And then remember that, here I left out a parenthesis, so let me put in the parenthesis. You have then 1 over 1 plus z over 2 is just 1 minus z over 2, approximately, for small z. And you multiply that out, you get 1 over z as the singular term, minus a half as the first correction. So these are the two that I circled in red. But Matlab gives you the next two terms, z over 12 minus z cubed over 720. Now, suppose you wanted something else. Suppose you wanted more terms. Well, then to get more terms, you insert after the z, forget about expansion point 0. After the z, you put a comma, quote, single quote, order, single quote, comma, and then whatever the order is, some number like 8, 10, 15, whatever. And then instead of these 4 terms, you get these 4 terms plus z to the 5th over 30,240, and then a z to the 7th term, and then z to the 9th term. And now suppose you wanted the series to start not at 0, but at some other point. Well, you put then quote expansion point, one word with a capital P, quote, comma, and then whatever the value of Z is, and then it will do that. I did it for the case, let's see here, if I can show you it. I did it for the case expansion point 1. So I did series 1 over e to the, oh, that's square root of Z. Why did I do square root of Z? Why in God's name did I do square root of Z? All right, well, let's do it the way I just said. So let me series, and I can save some of this space. So let me put in some of these spaces here. So there I don't want square root. So let's get rid of square root. So series that expansion point order 6. Okay, that sort of makes sense. And so what you see here then is that it gives you an expansion point about 1. So here we have Z minus 1 cubed. Here we have the value of this thing for Z equal to 1. And that's 1 over e to the 1 minus 1. And then we have all these other terms, and they become quite lengthy, as you can see. And in fact, this thing goes on for quite a ways. So you can get extremely lengthy expressions here. Let's ask Matlab to do it, but not with order 6. Let's say order, let's let it decide what to do. Now, well, it's just as bad, frankly. Look at this. All right. So you can get very complicated expressions from changing the expansion point from what is a natural expansion point. All right, let me switch now and do another example, but this one is one that I mentioned briefly in class, but I didn't do it in detail. And in fact, doing one of these in detail, I realized that in fact, there's something a little silly in my description here. You see, the integrating factor here, I say, is, so we're talking about a linear first order ordinary differential equation. This is the general form. And what I said was, in the book, you can always find an integrating factor that makes this exact, okay? And of course, what you do is you get this as the equation. So then I integrate it this way. Well, it turns out, if you just look at these equations, they're all homogeneous in alpha. So you can always set alpha of x0 equal to 1. So you can always set alpha equal to e to the this. So you don't need to fool around with alpha of x0. And you can see that because over here, alpha of x, well, it's proportional to alpha of x0. So the alpha x0 cancels. And here you have also the alpha of x0, of x prime canceling the, the alpha of x0s cancel. So you can always set them equal to 1. Of course, what you get finally is the same equation. You still get this exact equation, but up here, I think it'd be a lot simpler if we just always set alpha of x0 equal to 1. So just alpha is just e to this integral from whatever x0 is to x of r of x prime dx prime. So I thought I would do that explicitly in the case of this simple case of bodies falling in air, and to look at it in real detail, the equation, and in fact, what we can do is, since we've got these double screens here, we can just compare the equation, which is, it's m dv dt plus bv equals g, m, but you divide by m, you get dv dt plus bv over m equals g. And so over here, you see, I did unfortunately have an alpha of x0, so I can fix that in a jiffy here. I think, oh, that's right, I have to use the screen. I've got so many screens here, I can lose track. So let's just do this, setting alpha of 0 equal to 1 just identically. This just cleans up the equations, and you get the same answer, of course, but I'll just put a 1. Whoops. So that's cleaning up the equations. That's what it looks like. So in other words, you said, I said v of 0 equal to 0 because I was thinking of something being simply dropped. So falling body starts at speed 0, where it's when it's being dropped. And the coefficient of v is called r, and the inhomogeneous term is called s. And so the recipe is v of t is 1 over alpha of t, integral from 0 to t of, and what does it say? Well, the answer here is e to the alpha. Well, alpha is e to the bt over m, so it's e to the bt prime over m times s. S is g, so you get g here. You do the integral, you get that, and you can write it in these various forms. Another simple example here is a simple circuit where you have an applied voltage across a capacitor in series with a resistor. And then, once again, I'm going to set alpha of 0 equal to 1. And that's going to just make everything a little bit simpler. So and so what you have to start with your equation here is I dot plus I over RC is V dot over R. And so then alpha is you see, alpha is the integral of R, and R being this function of R, and this function of R is just 1 over, this alpha is just an integral of just 1 over RC, so it's just e to the t over RC. And so 1 over alpha is just 1 over e to the t over RC, and then I of 0, so going back to here, I of 0 plus the integral, and then here you have the inhomogeneous term, which I'm taking as given, V dot, V of t is the applied voltage. So V dot of t prime is given, you divide by R, and then you have the integral of, you have alpha of t prime, and that is effectively, it's e to the integral up to t prime of this, which is just e to the t prime over R C. And so this is our answer, and that's the answer that occurs here. I think I'm going to skip the fluorophore business. Here is something that I think I might have mentioned to you briefly last time, namely that Matlab can solve differential equations. And in fact, it does a remarkable job at this. I find that more impressive than almost anything else it can do. So you say Sims y of t, you say your ODE is the derivative of y with respect to t. That's going to be log of t over 1 plus t times y. So in other words, we're translating this differential equation. So let's switch now to this, hold on, to this example. And so we're saying here, Sims y of t ODE is, so that is dy dt is equal to log t over 1 plus t times y of t. Now, this is kind of a scary differential equation. If we did it by hand, we'd say dy over y is equal to log t over 1 plus t dt. Well, so we've separated it. We can now integrate. We get log y is equal to this integral, but I don't know how to do that integral. Log of t prime dt prime over 1 plus t prime 0 to t, say, is log y over y of 0, y of t. And so y of t is y of 0 exp of integral 0 to t log t prime dt prime over 1 plus t prime. So that's what I can do with my fingers, but I don't know what the log is, what the integral is. And so when you say this to MATLAB, it then replies ODE of t is this, and double equals means human equals, so to speak. And you say a condition y of 0 is going to be 1, and then you say y sol of t, this is just your name for the solution, is d solve of ODE cond, this with this boundary condition, and it does the integral. And what is the answer? Well, you see, it's an exp the way I said, and it said that y of 0 is 1. Here I left y of 0 arbitrary. If you set it equal to 1, then you just get an exponent. Well, apparently this funny integral is the polylog of 2 and minus t plus log of t plus 1 times log of t. The polylog is one of these standard functions, and you know, there are just infinitely many standard functions of mathematical physics that have been worked on and worked out. So the next topic here is small oscillations, and normally, if you can imagine the world classically or quantum mechanically, you have some ground state, and you can have then infinitely many excited states. And for example, the early universe was a pretty excited state, and very hard to describe. On the other hand, if you describe empty space now, then it's, at least in conventional simple variables, it's pretty simple to describe. And so, for example, if we're talking about a mechanical system like a harmonic oscillator, then we'd say classically the ground state is the thing is here, and then there are various other ways in which the thing can, for example, go from here down up to here again, or it can go from maybe here down up to here again. These are classical oscillations. And then quantum mechanically, you know that what we have is the lowest state, which is h bar omega over 2, and then we have h bar omega 1 plus a half, and then we have h bar omega 2 plus a half, and so forth, and you have just an infinitely many excited states of the harmonic oscillator. Well, the point here is that if you have, you see, an arbitrary potential V of, well, I better use the same variables that we're talking about here. What am I talking? Q, V of Q. So this V of Q, what is it? It might be something like that. But if you look at, if you take the minimum here, which is, let's say, Q0, then near the minimum, V of Q is going to be V of Q0 plus V prime of Q0 times Q minus Q0 plus a half V double prime of Q0, Q minus Q0 squared plus higher terms. Well, the first correction here vanishes. V prime of Q0 is 0 because Q0 is a minimum. And so what we have then is that V of Q is V of Q0 plus a half V double prime of Q0 times Q minus Q0 squared. Oh, that's terrible. Hold on, let me just undo that. So let me just try to make the minus sign a little bit. So what this is saying is that if you have a problem in one variable, an arbitrary potential, very hard to analyze. But if you look at it near its minimum, assuming it has a minimum, if you look at it near its minimum, and of course assume Q is smooth, so we have derivatives that are smooth and so forth. We go down there to the minimum at the minimum here. Oh, damn it. I can't tell which screen I'm on. The minimum around Q0, near that, it's simply quadratic. And consequently, what you've got is a harmonic oscillator at Q0. And if you look instead at so the whole thing then near the Lagrangian, well, if you suppose you have not just one variable, but suppose it's a particle in 3 dimensions rather than 1 dimension, then what you would have would be V of Q vector is V of Q vector at 0 plus a half, and now it would be V sub XX times Q, well, all right, maybe I shouldn't have said XX, so let me do a few of these. So I'll say V of 1, 1, and it would be Q1 minus Q10 squared plus a half V 1, 2 Q1 minus Q10, Q2 minus Q20, and so forth. So you have a bunch of terms, and the last term is a half V33 Q3 minus Q03 squared. Right, so you have all these different combinations. In other words, you have a quadratic form in the second derivatives, all evaluated at Q0. So this is at Q0. And so this becomes just a bunch of harmonic oscillators, and these things are the normal modes. And, you know, when you have a, if you have your Lagrangian, let's go back to one dimension. So it's 1/2 m, and for some reason I wrote this as s. All right, let me get rid of that last thing. S dot squared minus a half v double prime s squared. If that's your Lagrangian, then the solutions are s of t is some a cosine of square root of, let us see, well, it would be square root of v double prime over m times t plus some b sine square root of v double prime over mt. So this would be what your solution would be like, solutions would be like. And it turns out that that this is true not simply of mechanical systems, but also of fields, electromagnetic fields vibrating about some minimum. And in fact, we often would write these things as some z e to the I square root of v double prime over m t. And in fact, you can write classical fields then as sums over the normal mode frequencies, or integrals over the different momenta and so forth. And as you make a transition to quantum field theory, you have the same business. They're all harmonic oscillators. And in fact, the harmonic oscillators are classically, you can have any strength at all. Quantum mechanically, you just have one of these quantized levels, which corresponds to 1 photon, 2 photons of a given mode. So let me now go to this next topic and see if I can maybe do a couple of examples here. So the first thing is this business of systems of ordinary differential equations. And I encourage you to play with this. Those of you who want to go further with this, I'd really recommend playing with this on Matlab. So a system of n first-order ordinary differential equations should look like this. And we say this system is autonomous because there's no time appearing explicitly. On the other hand, these first-order autonomous systems are extremely general, because you see they can represent systems that do depend on time explicitly, and also systems of higher order differential equations. So enormous variety is possible here. And suppose we want to make a system of n equations here with time derivatives autonomous. What we do is we set t equal to xn plus 1, and instead of having these, what we have is fi of x1 x up to xn, and then xn plus 1 is just t. So we just write it this way. So it's just a higher order system. It's a system of n plus 1 equations. And then the last one is fn plus 1 is, we just make that one the equation that says that x dot sub n plus 1, which is t dot, or the time derivative of t, is just equal to 1. And the way you can do that then, for example, in this particular case, if you have this as your time-dependent differential equation, you would write it this way. You'd say x1 dot is minus x1 cubed plus the cube of the sine of x2, and then you say x2 dot equals 1, and in that way, and you said x equal to x1, t equal to x2, and so you've represented this differential equation as an autonomous system here. And you can do the same thing with by making you can make a higher order differential equation, for example, not a first order, but a third order differential equation that's nonlinear. You can just make you can do it this way. You set x1 equal to x2 dot, x2 equal to x3 dot, and x3 equal to x. And so then your equation of this form becomes x1 dot equals, well, what is x1 dot? Well, x1 dot is x2 double dot, and x2 double dot is x3 triple dot, but that's x triple dot. And that's the way you make them, that's the way you make it work. And in this example, I took this these second order nonlinear differential equations, turned them into a first order system, making these changes, and it then gave me this expression here. Let me see if I can maybe go to this GitHub or GitHub, whatever the hell it's called. Let's see if I can do that. I just knocked something over, obviously. So let's go to this here. See if I can. I thought well, there it is. I just clicked on it and it went there. Let me move the chat. So we want to go to differential equations. So let's look at the repositories. Differential equations. So here I've gone to this differential equations, and what was the name for this one? I think it's probably 4 wells. So let's see if I can bring it up. So apparently this is the yeah, that's what it looks like. This is the differential equation. And so what you can do is you can take all of this and enter it into Matlab. Well, let me see if I can copy it and stick it in Matlab right now on the fly. So let's just see if I can get. Now, if I just hit return, what happens? Errors. Uh-oh. Well, all right. I don't want to do errors. Okay. Well, anyway, you can obviously one needs to play with this a little bit. Maybe the thing to do is to do a new script and put it here. And let's just try run. So I'll call it, I'll just call it class and save. Whoops. Oh, Christ. All right, it doesn't want. All right, so let me try run again. Hell, I need to change its name. I don't know why. All right, look, I guess that was premature trying to do that. So let's just go on. We defined exact as an equation, a differential equation. We said it was exact if it was d something. So here, an nth order ordinary differential equation that looks like this is exact because it's d of something. And as an example, here's a d by dx of y prime plus x squared y. So in this form, it's obviously exact, but in this form, it might not be obvious to you. Certainly isn't obvious, but now that you think about it, you see that this is the same as that, and so it is exact. And so you can solve it by you integrate first this first order equation where c is a constant using the method that we have that always works for first order equations, and then we get this expression. Here's a more complicated structure, and this exponential turns out to be an integrating factor for this equation, and then one can again solve this. Once you multiply by e to the x, you then get something that is exact because e to the x is an integrating function for this. But you know, it's in differential equations that the problem is, you see, how would you know that e to the x was an integrating factor? And so there's a lot of guessing that's involved, unless you have a turn the crank method, or you use Matlab or whatever. One class of equations that's pretty simple to deal with are what can be higher order differential equations, but they have constant coefficients. So this is kind of simple. You just say y equals e to the zt and do the derivative k times, you just get z to the k. So you then can you can factor out the exponential and you just have a polynomial equation. Well, we learned that every polynomial equation has solutions, and if it's nth order, it has n solutions. And so you then write y of t then is e to the zi of t, where zi is one of the roots of this polynomial. Let's see, I can probably do that as an example. So let me see if I can do this as an example. Suppose we have the equation 0 equals y plus, let's make it really simple, y prime plus y double prime. So then what would we do? We would say y is equal to e to the zt. So we'd have 0 equals e to the zt plus z e to the zt plus z squared e to the zt. We factor out e to the zt and we get 1 plus z squared. Well, this is a quadratic equation. The roots are z is equal to -1 plus or minus the square root of 1 minus 4 over 2. So this is z is -1 plus or minus, that's I times square root of 3, isn't it? Over 2. And so the solutions are y of t is, say, a e to the t time e to the minus t plus I root 3t over 2 plus b e to the minus t minus I root 3t over 2. So that's how this would go. And in more complicated cases, I think we can skip this. In more complicated cases, well, it's more complicated. Here, if you have a fourth order equation, you then get, well, this one was particularly simple. no, this is an example of this previous trick here, I guess. All right, so let me skip on to Euler's equations. If you had an equation like this, it's called an Euler equation. Well, this is quite specialized. So so here we have an LCR circuit. This is the voltage across the inductor, across the capacitor, across the resistor. Well, I may have gotten the, anyway, you get this differential equation. And well, this one, let's see. Oh, we have an applied voltage though. So this is the differential equation, but I don't see any solution here since we have an arbitrary function here. All right, so let me look at that in the future, but not right now. So let's go to second order ordinary differential equations. And this is the case that occurs very often in physics. And part of the reason it occurs very often in physics is that if you're, we just explained, if you're near the bottom of a potential, the first derivative will vanish. And so what you will have is the Lagrangian will be basically a quadratic form. And so you will have a second order differential equation. Or to put it differently, almost all the Lagrangians one deals with in elementary physics are second order in first derivatives. In other words, your system has a Lagrangian that's almost always the form qi dot qj dot times cij of maybe q and t plus other terms. So you almost always have second order differential equations. Because after all, when you took if you applied Lagrange's equation to this, you'd have something like d by dt of partial L partial qi dot equals partial L partial qi. So what you'd get here would be d by dt of qj dot cij of q and t equals, and then whatever this partial L partial qi was, I left out the other terms, v of q well, v of all the q's, let us say. And d by dt of that then is q double dot j times cij plus q dot j c dot ij equals partial L partial qi. So you almost always have second order differential equations in physics, and when in mechanics, classical mechanics, in Maxwell's equations, and also in quantum mechanics. And in quantum mechanics, what you've got is the Hamiltonian. In the simplest case, it's p squared over 2m plus v of q. And so p squared over 2m gives you minus h bar squared over 2m d2 dx squared, or dq squared actually. So dq squared plus v of q. And in 3 dimensions, it's h is equal to minus h bar squared over 2m grad squared plus v of r, say. So you almost always have second order differential equations. And So before studying them, we need to define something about regular points and singular points. And if the second derivative is finite at a given point for all finite values of the first derivative and the function, then we say that the point x0 is a regular point. But on the other hand, it's infinite, we call it a singular point. And then if it's a singular point, you say, well, if you have a, so let's see. If P and Q are both finite, you have a regular point. If they're both, one or both is infinite, then it's a singular point. And some singular points are regular, and that's that P or Q might diverge. But if x minus x0 times P and x minus x0 squared times Q are finite as x goes to x0, then x0 is a regular singular point or non-essential singular point. On the other hand, if either one of these diverges as x goes to x0, then you're talking about an irregular singular point, or one says an essential singularity. I'm going to skip the point of infinity. So let's look at Legendre's equation. So this is 1 minus x squared y prime, and then the derivative of all of that, plus LL plus 1 y equals 0. And this occurs for angular momentum. And multiplying it out, we get an expression like this. Or if we divide, we get y double. To find out what a y double prime is, we see it's these two expressions here. Well, obviously, when x is equal to plus or minus 1, we've got y double prime going to infinity. But these are actually regular singular points, which is to say that if you multiply by, for example, 1 minus x squared, in fact, maybe I can even just do this for you. I'll do the exercise. We can write this as y double prime minus 2x. Of course, if you factor this, this is 1 minus x, 1 plus x, y prime plus L plus 1 over 1 minus x, 1 plus x equals 0. So if we're looking at the singular point x equals 1, well, if we multiply by x minus 1, then you see what remains is just this and this, which is finite at x equals 1. On the other hand, if we're worried about the point x equal to minus 1, then we multiply by 1 plus x, and then we're left with these terms, which are finite when x approaches minus 1. So the singular points of Legendre's equation are both regular singular points, and the fact that they're regular singular points should be no surprise, because Legendre's equation wouldn't be so famous if it had irregular singular points, which of course would cause everybody a lot of trouble. Now, Frobenius provided us with a general way of solving these equations, or expressing the solution as an infinite power series. And so we imagine we have a differential equation like this, but we're going to rewrite it so it looks like this: x squared y double prime x p of x, little p of x y prime, little q of x y equals 0. And we're going to expand about some point. And to make things simple, we're going to expand about the origin, x equals 0. So we're looking for a solution like this. You can write it as y of x is x to the r, sum an x to the n starting at 0, or you bring the x to the r inside, you get that. And of course, one assumes that alpha sub 0 is non-zero, otherwise this equation would be kind of silly. You'd pull one of the x's out and have r plus 1 here. So what you do then is you differentiate this equation, and you differentiate again, and so you get this equation, that equation, and that equation. Then you take them all and you shove them into the original equation, and you get this. You get this after some work. It doesn't happen instantly. And then you say, well, we want the, whoops. All right, hold on, we want this equation to be true for all values of x. Well, if it's to be true for all values of x, then all of these coefficients have to vanish. So in other words, what you get at this point is that every an must equal 0. So you must have, let's switch to blue maybe, a sub 0, well, a sub 0 is not equal to 0, of course, but you need the coefficients, I'm sorry, you need the coefficients here to vanish. And so all of these coefficients, in other words, n plus r, n plus r minus 1 plus n plus r p of x plus q of x, this must vanish. And let's look at the lowest case, which is the simplest one. So we set n equal to 0 here. And what we get from this equation requiring the coefficient of a0 to be 0, because we know some of the ans could vanish, but by hypothesis, by construction, a0 is not 0. And so for n equals 0, what we get here is r times r minus 1. Whoops, no parenthesis, hold on. R times r minus 1 plus p of 0 plus q of 0. So that's what comes from this. And this is a quadratic equation in R, and this is called the indicial equation. And so what you do is you solve for R. And so that's a quadratic equation. So it's r squared plus, I'll call it p0 minus 1 times r plus q0 equals 0. That's the, so it's this, we want to set that equal to 0. So if I haven't made a mistake here, right. And so we said r is equal to 1 minus p0 plus or minus the square root of p0 minus 1 squared minus 4q of 0 divided by 2. And these are the two roots then. And then if you require that the coefficient of x to the r plus k should vanish, you then get a recurrence relation. You get an equation that determines rk in terms of all the lower ones. And when p and q are polynomials of low degree, these are pretty simple. And when the roots are complex, the coefficients are also complex, and the real and imaginary parts, the complex solution, are actually two solutions of the differential equation. So I'm just wondering what to do. Maybe I should do exercise 7.21 for you, because that looks like a bit of a bear. So let's go to 7.21 and see what the solution looks like. Well, it doesn't look all that hard. Anyway, all right, so let me show you what's involved here. So what we want is we want to solve this equation. And what we do is we replace P of X by its form. It's in general an infinite series. Q is in general an infinite series. And so we want the coefficient of X to the K plus R. And that coefficient then turns out to be, so we substitute for, in this sum, we set n equal to k. And so we get here this sum well, setting n equal to k, we have k plus r minus 1 times a sub k. And then we have this term, all these various aj's. And all right, well, I must say this is a little bit hard to absorb on the fly. Anyway, we set that equal to 0, we get this expression, but it's not immediately obvious to me how this works, because we have double sums here. Yeah, so I'm gonna I tell you what, I will send you this solution, but I don't think I'm gonna puzzle through it here. It's looks a little more complicated than I thought. Of course, in some examples, it's some simple examples, it is pretty simple. If we have y double prime plus omega squared y equals 0, we can write it in this form, and we see P is 0, Q is equal to omega squared x squared. So P of 0 is 0, Q of 0 is also 0. And the initial equation then is this equation. Both of these guys are 0, so it's just r minus 1 equals 0. The roots are r equals, well, the roots are obviously 0 and 1. If we set r equal to 0, the p's and q's vanish, except for q2, which is omega squared. And so then we go back to this equation, and we have that ak is ak minus 2 times minus q, and p0 and q0 both vanish. So this is, we just divide by k minus 1, and that's then omega squared ak minus 2 over k minus 1. And so the setting k equal to k equal to 2, we have 2 times 1, a0, and so that tells us that a2 is minus omega squared a0 over 2. A2n then if you iterate this, you get -1 to the n omega to the 2n a0 over 2n factorial. And so then we just find that we can set a1 equal to 0, and then all the odd a's are 0, and so we just have y of x as a sum of omega x to the 2n like this, and that's the cosine. And if you do the same, use the second root, r2 equal to 1, you then get the odd terms, and a2n then is a0 omega squared to the n -1 to the n over 2n plus 1 factorial, and plug that in, you get a sine. And so so what you get is, by the Frobenius method, is you get ways of constructing power series for your differential equations. And an important point in the case of quantum mechanics, I don't know. I mean, this may occur in classical mechanics. I never saw it in classical mechanics. But it certainly occurs in quantum mechanics. In fact, it's the essence of quantum mechanics, namely that when you do Frobenius's method and you go back here and you get, where's the final solution? I should have an equation with the final, so that's too bad. I have it for the examples, but not for the general case. Well, all right, here. So we eventually are going to set y of x equals this, and x to the n, an infinite sum, a sub n, x to the n. So then we get recursion relations for the ans. And then we look at this series. And what often happens is, so let me switch maybe to blue, in quantum mechanics is that y of x then is some x to the r, some a sub n, x to the n equals, let us say, 0 to infinity. And we find out what the ans are, I should say. Well, suppose all the ans are equal to 1. Then y of x is x to the r sum x to the n, and this is x to the r 1 over 1 minus x. Well, that's fine if your physical region, let's draw the, here, I'll draw the x-axis here, and this is y, and this is, I'll put a point here, -1, +1. If your physical region is confined to this part of the, actually, let me get rid of that. That was a stupid thing to do. I meant to go to, if the physical region is between the two yellow marks, then this is a fine solution, 1 over 1 minus x. But if this is to be a solution for all x, well, and you know, in quantum mechanics, what you need is you want to be able to say that 1 is equal to y of x absolute value squared dx from -infinity to +infinity. You want the thing to be normalized. So that's not going to work if y is 1 over 1 minus x. So basically, so what does that tell you? That tells you that the series has to terminate. And so now I just said to you immediately that all the ends were just 1 equal to 1. But what happens in general is that let me put it this way. Y of x is all right, let me undo what I just did. Y is equal to x to the r, a sum, an x to the n equals 0 to infinity. This turns out in quantum mechanics to be something like this. And these are ANs of the parameters of the theory. So parameters, x to the n. And in particular, they might be of this form. Something like the ground state energy, the angular momentum, the mass, whatever, x to the n. And what would happen is that these coefficients, the formula for the coefficients would be such that you could see that this would not give you a square integrable function unless the coefficients terminate at some point. And that then gives you a condition that, say, a sub k of E0, L, and M has to equal 0. And then the recursion relation tells you that all the higher coefficients also vanish. So the series terminates, but this is a quantization condition. And in the hydrogen atom, the condition is that En is minus a half mc squared alpha squared over n squared, where n is an integer. Well, I imagine you've always seen that, but the way it shows up is then when you apply Frobenius's method, you get this sort of problem. Now, let me see if there's anything in the chat session here. I don't see the chat session. Oh, there's the chat session. I don't see any questions in the chat session. So that's how the Frobenius method works. Suppose we apply it to Legendre's equation. I think maybe we have time for that. So then we first of all write the equation in this form. And then we divide through by x squared, and we find that p of x is minus 2x squared over 1 minus x squared. Q of x is x squared lambda over 1 minus x squared. And that's by writing this equation this way. So P and Q are analytic, but they're not polynomials. And so what we do is we substitute the expansions for y prime and y double prime into Legendre's equation directly. So in other words, we just grab Legendre's equation here and then stick the thing in. In other words, we say y of x is just a to the r sum on n a sub n, or a0 to the r. No. Well, that's r to the n, isn't it? Yes. All right, hold on. So I've let me use the eraser. It's r to the n. So it's r to the n, r to the n plus r. And let me just make sure I'm doing this correctly here. Right, r to the n, an. Oh, it's not. I'm sorry. I've been interchanging r variable with r function. So let's go back to. Okay, so that's y. This is going to be x to the n. X to the n plus r. And we just substitute this directly into Lagrange's equation, Legendre's equation, 1 minus x squared y double prime minus 2xy prime plus lambda y equals 0. And if you just substitute the infinite series in, you get this infinite series. And now you look for the lowest power of x, and it's again r minus 1 x0. And so you again get the same initial equation that r equals 0 or r equals 1. For r equals 0, you now substitute r equal to 0 in here. And you then want this thing to be, want all the powers to be the same. And so you shift n to j plus 2, and you set n equal to j in the other terms, and then you manage to get this expression, x to the j, and this coefficient in this curly brackets here. And that is the recursion relation then. Aj plus 2 has to equal this, Aj times these things divided by that. And so you get this recursion relation. And now if you look at this for big J, so here's the quantization condition. For big J, you see you have J squared over J squared. So that's going to be a series that's going to diverge, let alone be integrable. Consequently, this thing has to vanish at some point. So lambda has to be Jj plus 1 for some integer J. And that then gives you the Legendre polynomials. So that's basically how that works. So tomorrow we'll start at 5:30. We'll Zoom again, and I'll just do examples tomorrow. I think it'd be absurd for me to do the homework problems, but what I can do are examples that are adjacent to the homework problems in the back of the book, and other problems that are similar to the homework problems, or just other problems, because after all, I certainly did not mean to pick the hardest problems as homework problems. Okay, so we're basically out of time. I'm going to stop sharing and recording. I'll put this on YouTube, and you'll be able to view it, I guess, late tonight. Hold on. Okay, so somebody liked the Matlab examples. I'm glad to hear that, and I will keep that in mind then. Tomorrow I will try to do some Matlab examples. And as I said to you, some of them are really a lot of fun. It's just amazing what Matlab can do. And then if you plot it, you get these amusing diagrams, amusing figures. And so that's I find that amusing and interesting. All right, so I'm going to stop now. And you guys can send me email. The email address is on the website, and it's just my last name at unm.edu. And you can say you like MATLAB examples, or you don't like MATLAB examples, or you'd rather I do this or do that, or emphasize this or explain that. I'm not a very good listener, and I'm a terrible mind reader. So you've got to send me email or say something in chat so that I understand what it is that you want. All right, so I'm going to stop now.